Now, Kirchhoff's law is the law that governs the electrical electrical transmission in a DC circuit. The first law simply say that the total current inside any point, must be the same with the total current that is going out of that point. This is the symbol sigma, and that is the sum of in physics. Sum of the current in equals to the sum of the current out in any point. So if you have any single point here, the total current in must be the sum of the current out. This goes in any condition, including junction. If you have any junction here, current in must be the same with the current out. You can have no matter how many junction here, how many points in out a point, how many lines in out a point, but the total in must be the same with the total out. Having said that, okay, can I ask you to go to page 145 and find me the current in question 1. Nicholas. Oh, sorry. Nicholas already called, right? Okay.
Yeah.
Shovel, please go to page 145 in your textbook and find the current in question number 1. We have here. Shovel, are you there?
4.5.
4.5. Very good. Okay. Okay, then Tessa, what about question number 2? There is one wire there. We don't know the current. Is the current going in or going out? And after that, what is their current value? Tessa? Is Tessa present here? Tessa, it's your turn now. Question 2, page 145.
1.5.
1.5. Okay, and how you got 1.5? The direction, please. In or out? That's more important.
Out.
In or out? Into the point or out from that point?
In.
In. Okay, why is that so?
Because more current going in than going out.
Okay, because initially without that, there are more current going out than current going in. So they help more current going in to balance the number. Before that, what we have is in, we have 3.0 plus 2.5, and out we have 7.0. This is smaller than that one. So if there is another one, it should be located here to help balance the equation. Good. So Kirchhoff's first law comes from the condition of conservation of electron. The current is just electron. We cannot create electron, nor can we destroy it. So if there is electron going into one side, that electron must go out somewhere. Okay, now, this is the first law.
Sir, why 3 plus 2.5 equals to 7, sir?
This is before the extra wire X. So the extra wire X must be here to make them balance. Before the wire here, before the addition, we have only these 3 number with these 3 wire with known direction. In order to balance it, the last wire X must be on the inside part, not on the outside. This is already lower than out, right? So if you put them there, we cannot be balancing. 5.5 plus 7 cannot be 7 plus something else. So it has to be there. Okay, Kirchhoff's second law. Kirchhoff's second law is about the energy. Remember what is electromotive force? It's about work done. work done is from something else. From the point of view of the electron is about the energy gain. If something else is doing work on electron, means the electron is going to gain energy. While the potential difference is about the energy lost. Energy lost by electron. Now, because energy must be conserved, energy gain must be the same with the energy loss. Put mathematically, sum of the electromotive force must be the sum of potential difference is I times R. This is how we have the Kirchoff's second law. I repeat, the total energy gained by a charge as they go in a loop is the same with the total potential difference across that loop. Okay. That is because of the conservation of energy. So the energy in any loop must be the same with energy loss in that loop. Sometimes they call them sum of the V, but because we almost always put them as I times R and no other forces of voltage, I put them I times R for simplicity. Okay, that is the simple one here. Kirchhoff's laws is often used simultaneously. So we often need to deploy both of them to solve a particular question. Okay. I'm going to erase this, yeah? Let's see some application of this. On page 146 here, we have this information. We have a battery here, okay, and the total is 6.0 volt. And we have here two conditions. And this is 2.0 volt. So we have here two EMF. Now, this is 30 ohm, and this one is 10 ohm. Next, they are given us the current. The current goes here, they call them current number 1. The current here is going to be current number 2, and the current there is going to be current number 3. Now, please check that the current is going to be the same because of the Kirchhoff's first law. As long as there is no branching, the current in a particular wire will always be the same. So the current number 1 here and there up until this point is still current number 1. So here is current number 1, and here this is still the part of the same wire. That's going to be current number 2. Now, if I call this point P, Leon, make me an equation of current at point P. Give me equation relating currents 1, 2, and 3. Is Leon Lim here present?
Yes, sir.
Okay. So, based on point P here, make me equation that is relating current number 1, current number 2, and current number 3. Use Kirchhoff's first law. What is Kirchhoff's first law in word?
Kirchhoff's first law is the sum of the currents entering any point in the circuit is equal to the sum of the currents leaving the point.
Okay, now, which one of this is the current going into P?
Into V is I3.
No, into P is I1 and I2. The direction of the arrow is going to P. Did you have your textbook with you?
Oh, yeah. I just looked at it wrong.
So in this case here, sum of current in is the sum of the current out. The one that's going in is I1 and I2. So I1 plus I2 equals, what is the current going out then?
I3.
I3. So this is what we mean by the application of the Kirchhoff's first law. Okay. Current 1 equals plus current 2 equals current 3. I1 plus I2 equals I3. Good. Now, we have several loops here. There are 3 possible loops. We can put them here. Okay. I'm going to call the point here point A, point B, point C, point D, point E, and point P. One of the possible loop we have is APCB. That is one of the loop that we can have, APCB. Now, in loop APCB, we are going to apply Kirchhoff's second law. The total of the EMF is the total of the current times resistance. There is only one here, the EMF, only 6. So 6, I'm not going to make them 6.0, just 6 to simplify, is going to be the current. There are current here and current there. We have only 2 resistance. So that's going to be I3 times 30 plus, this is going to be I1 times 10. This is how we make them in this one here. I repeat, current 3 times 30 is the same way, plus current 1 times 10. The status of current passing through this one is current number 3. The status of the current passing 10 ohm is current number 1. With the same idea here, we can make another one, which is the loop EPCD. EPCD. Now, EPCD, Brandon, make me the equation of Kirchhoff's second law in the loop EPCD. What is the EMF? 2.
2 equals to I3 times 30.
I3 times 30. Very good.
So that the sigma is sigma I and R, yeah, sir, together. Yes.
Sorry? Sigma?
Not sigma I times R, not sigma I.
No, that's sigma IR.
Okay.
Yes, correct. Okay. Now in EPCD,
What
we
is
have
F?
2.
What is the F?
Now, what is the F? What? What F?
The F symbolizes what?
There is no F here. What F?
F3 times
Oh,
30 plus.
that is I. I3. Okay, next. Christopher, name the third loop we can have here. I gave you loop APCB and loop EPCD. Give me the third loop there.
A, B, D, E.
Good. A, B, D, E. Now, Darwin, give me the equation for the Kirchhoff's for the loop A, B, D, E. We're going to work this way.
6 plus 2.
Sorry?
6 plus 2.
Here. In this case here, as we go from A to B, we are going against the 6.0 volt. So we're going to have negative 6. Negative 6, yes, plus 2, very good.
Equals to I1 times 10.
And it's going to be negative I1 times 10. Why negative I1? Because here we're going to go against the direction here. The direction goes there, right? If we have them A, E, D, B, then the 6 is going to be positive, it's negative, and it's positive. We go along with the direction. But as we go this way here, then we're going to go against the current in this point. So the number is negative of I1. We go against it, times 10. Now, up until this, we have then 4 equations. This one, this one, this one, and this one. 4 of them. And we can use that to find out the 3 currents, I1, I2, and I3. Now, from here, it is easiest to see that in question number 2 here, APCD, we can find current number 3. So current number 3 is going to be 2 over 30. Now, from here, we can use current number 1. Next is Derwin, right? Derwin or Devanya? Who's next? Derwin? Okay. From this equation,
Devanya.
Me, sir, me.
Oh, okay. Devanya, find me current number 1 by using this equation.
I1 is 4 over 10.
4 over 10. Good. Okay. Now, the only one we don't have them yet is now current number 2. Okay, and Eugene.
Why didn't we use negative 2? Why don't we make the direction of the current from EDBA?
Because the one being asked is A, B, D, E.
It's the same. If you say EDBA, you're going to have the same here. That's going to say 6 minus 2 is 10 times I1. These two are equivalent. Okay. These two is equivalent. Same, yes. Doesn't really matter which one to use. It's just because you Christopher defined the loop as ABDE, not AEDB. If the loop that we define is AEDB, use this. It will be wrong. Be careful when you when in exam you are making the loop ABDE, but you write this. That's wrong. Okay. Be careful about the direction of the loop. Okay, Eugene, find me current number 2 then.
Eugene absent.
Eugene is absent.
Oh, absent. Oh, okay. Okay, well, I hope he can also. Edric then. Edric, find me current number 2. Hello? Is Edric here? No? Okay, if Edric is not here, then there is Edric here. Edric, hello? Are you there? Edric? Okay. If you cannot... sorry? If you did not... Yeah, if you did not respond, guys, then that will be a strong case to suggest that you're actually AWOL. Okay, that you're actually not going to school and you only just turn on your computer and leave. Okay, and that will be count as being AWOL, absent without leave. Okay, that will be the same as if you are not present in the class. Bolos, in short. Okay, so next that's going to be Farrell. Farrell, get me current number 2.
Yes, sir. It's minus. Is it minus?
Yes, it will be minus.
Minus 10 over 30.
Minus 10 over
30.
30. Okay. Now, if this is going to be, yes, 10 over 30, that's going to be 12 over 30. Okay, we are going to use this one here. Current number 1 is 12 over 30 plus I2 is going to be current number 3 is 2 over 30. So current number 2 is negative 10 over 30. Can current be negative? Yes, doesn't really matter. It means that we are making a wrong assumption of the direction here. The actual direction is going that way. I repeat, in this case here, when the calculation shows a negative value, it means that our assumed direction here is actually reversed. What is actually happening is the I2 is going there. This is what actually happening. So is it possible in real life? Yes, it's possible. Okay, this is actually what happens almost every day in your life. This will happen when you are charging battery. So current number, the EMF 2.0 volt here is not giving out energy. In fact, it is receiving energy from this one. This is a situation we call charging. So instead of the energy flowing out, energy was pushed into this. And this is what happened in the charger when you charge your phone. Okay, so that is a simple one here. Any question for this part? No?
So how did we get the equation for I1 again?
I1. Yeah. For the I1, we just use this one here. The 6 volt here is going to be positive because we go with the direction. But this one is going to be I3. I3 we have here. In this case, I'm using this from EPCD. I already erased it down here. 2 equals to I3 times 30. Okay, I'm going to erase this one. Anyone still take note? No? Do you have second in command, the deputy of Eugene? Is there any vice president, vice captain of the class in your class? No. Okay.
Wait, sir. There is. I'm looking it up.
Okay. Next, we are going to go into the concept of resistor in combination.
Vice President is Derwin.
Derwin. Okay, thank you. Derwin, next time when you see Edric, okay, tell him that he's supposed to respond to any questions for teachers. Otherwise, he will be recorded. He will be reported as being AWOL from the class. Okay. So, combined resistance. There are two ways we can combine resistances. The first is what we call a series. In a series here, the current must go through each of the resistor. Okay. So, if the current going here, That's A, then go to B, then go to C before going out. In a series resistance, a current will have to pass through all of them. The other one is the parallel condition. Now, parallel condition, then the current must choose between A or B or C or more. So this is, let's say this is A, this is B, and this is C. This is the parallel condition. Now, what is special in the series position? In the series position, because of the Kirchoff's first law, we have current in A, the same with current in B, the same with current in C. But what about the voltage? What about the potential difference? Now, potential difference total, V total is going to be VA plus VB plus VC. So in series, energy loss in A plus energy loss in B plus energy loss in C, that will be the total energy that was being lost as the current passed through it. What about the parallel condition? The parallel condition here, we know that the total current will be the same with the current total in. So if we take this as a single item, we have the voltage is times current resistance, right? The total resistance is going to be the reciprocal of the total reciprocal. 1 over R total is 1 over R1 plus 1 over RB plus 1 over RC. How come? Before we go this, let's see application of Kirchoff's second law on this loop. What happens if we apply Kirchoff's second law on the loop going from A to B and back and forth? If this is current A, current B, and current C. Going A here, I'm going to go against her. Negative A times resistance A plus IB times resistance B. This is the total of I times R. And that's going to be 0 because there is no EMF here. There's no EMF. So in this case here, that's going to be 0. On the right hand side, this is negative because I go against, and this is negative, positive. Now, if I move this, I get IA times RA is IB times RB. I repeat, current A times A, the same with current B times B. With the same argument, we can find that will be the same with current C times IC. The potential difference between in and out is the same everywhere. So we'll say that V and A, the same with V and B, the same with V and at C. So this is the difference between the condition in series and parallel. In series, we have same current. In parallel, we have same potential difference. That is for sure. I repeat, in resistance in series, the current is the same everywhere. In parallel,